Alright, welcome to the NUPOC video study guide number 64. We're going to take a little bit of a detour from the optimization section that we started in the last video for a little bit of a viewer request to take a look at some waves and oscillations problems. So if you go to the last section in the Navy study guides, the last section in the physics part of them, you'll see there's a couple of sections on waves and oscillations, and basically what they're talking about here is like differential equations that describe vibration and how waves reflect off different media, things like that. And one of the really traditional problems, a really fundamental part of waves and oscillations and vibrations and whatnot, are simple harmonic oscillators. Right? So when we talk about a simple harmonic oscillator, we're talking about traditionally, right, in the simplest case, we're talking about a mass spring system, right, where you have some mass here with some mass m, and we have a spring here with some spring constant k, okay, and it's anchored at one end, and we're able to sort of pull the mass down and release it, and the system will start to oscillate up and down like this, right? And we could sort of represent this same simple harmonic oscillator characteristic in other ways, for example with a pendulum, or with a circuit with an inductor and a capacitor, and the charge sort of oscillates back and forth between the two elements. So the first question in the waves and oscillations section in the study guides, right, asks for the period of a simple harmonic oscillator. And it would probably be good to know, just off the top of your head, that the period is just 2 pi root m over k. Okay, so if you have a larger mass, there's a longer period of oscillation, so it oscillates much more slowly. And if the spring, if k is very large, if the spring is very stiff, right, then it will oscillate much more rapidly, right? And that seems pretty intuitive. But let's go ahead and see how we would derive this, because an excellent follow-up question to asking, well, what is the period of the simple harmonic oscillator is, okay, well, go ahead and derive that for me, right? So let's go ahead and do that. So we would want to start by looking at the physical system, right? So we have this mass here, and we said we were going to displace it, okay? And we're going to release it, so I'm gonna like pull it down, right? And then I'm going to release it, and it's going to fly back up, the mass is going to shoot back up, and it's going to start oscillating about some equilibrium point. And this right here, this is the equilibrium point where it's at rest. So if I draw this same mass and spring over here, but now it has been displaced, I've pulled it down, right? Let's take a look at the net force, right? The net force on this mass. So it's like, let's draw a free body diagram on the mass, right? So let's just look at the mass, and let's go over here, and let's draw a free body diagram. So we know we have mg down, right? Force of gravity, and we also have, I want to divide the spring force into two different components, and that's really one of the tricks here, right? It makes it a lot simpler. I'm going to have this component here, and I'm going to say this is our x hat direction, by the way. And I'm going to say this level at the ceiling here, this anchor point, I'm going to say that's x equals 0. And this level, right, I'm going to say this is x naught, or let's say it's x1 so we don't get it confused with x equals 0 up here. So this is x1, and then this level down here after it's been displaced is x2, and the difference from the equilibrium position to the displaced position, I'm just going to call that x, okay? So when we draw our free body diagram here, this is after it's been displaced. So we have mg down, plus we also have, let's see, we have k x1 pulling it back up, because that's the spring force that we would see at equilibrium. So this kx1 balances mg, okay? So if kx1 is the only force pulling back up, then the mass is at rest here, because we know that this is the equilibrium position at at x equals x1, and we still have mg down there, and we have this kx1 pulling up, and we know we're at rest, there's no acceleration. So these two sort of cancel each other out in a way. They're still there, but they're equal and opposite, so they don't contribute to any net force on the mass. But after we displace it, we also now have kx, right? And x is just x2 minus x1. x2 minus x1 is just this difference here. So kx is the force from the displaced spring. And that is what is going to cause our acceleration back up in this direction, which would actually be the minus x direction, okay? Since x hat we've defined as going down on the page. All right. So now let's just, we have a sum of forces, and that kind of leads us to F equals ma. So let's write that out. So the sum of the forces in the x direction equals mass, the mass times the acceleration of the mass. And the sum of the forces, that's just minus kx, right? It's in the minus x hat direction, okay? So from here, where do we go? Well, we could say, well, we want something in terms of x, right? So we know a in terms of x, right? Because we know acceleration is just the second derivative of position. So let's go ahead and do that. Let's sub in the second derivative of position for acceleration, and we'll get ourselves a differential equation. So we'll have something like m d squared x over dt squared equals minus kx. Okay. Now I can just bring this kx to the other side and divide both terms by m, and what we'll get is d squared x dt squared plus k over mx equals 0. And now we can go ahead and solve this second order differential equation. And like we've done before in some of the differential equation videos, we're just going to assume a form for x and then take two derivatives of it and go ahead and sub back in. And then we're going to do the method of undetermined coefficients to see what the frequency of oscillation is. And since we want frequency, we're looking for omega frequency, right? We want to choose x, we want to choose the function, our function for x. We don't want to choose it to be an exponential, we want to choose it to be a trigonometric form, right? Because trig and exponential forms are the two typical solutions for a differential equation. So we want to choose one of them, and in this case we're going to choose the trig form, since it's a little bit more convenient for what we're trying to find. So I'll say that x of t, right, is equal to, let's just say, some constant a cosine omega t plus some constant b sine omega t. Okay, so now I'll just call this x prime of t, right, equals let's see, minus omega a sine of omega t plus omega b cosine of omega t. And when I take the second derivative, so x double prime of t, which is acceleration, right, we will get, let's see, minus omega squared a cosine omega t minus omega squared b sine of omega t. Okay, so now let's go ahead and sub in x and the second derivative of x here. And what we'll get is, let's see, minus omega squared a cosine omega t minus omega squared b sine omega t, right? And we will have plus k over m times x. But I'm just going to go ahead and move that to the opposite side of the equation, right? So we're going to say this equals, right, this is the second derivative of x, this equals k over m times x, which is just this a cosine omega t plus b sine omega t. So I'm just going to distribute the km in, so we'll have a cosine omega t, right, plus, minus, gotta have a minus sign there, minus, because we moved it to the opposite side of the equation. Gotta keep track of your minus signs, of course. Minus k over m b sine omega t. So now we have a cosine term on this side and of the equation here, and a cosine term on this side, and same thing with the sine terms. So we just do method of undetermined coefficients. We match the coefficients on each term. So we say here that if we have a bunch of stuff times a cosine omega t here, and a bunch of stuff equals a bunch of stuff times cosine omega t over here, let's just equate those two coefficients. So we have minus omega squared a equals minus k over m times a. Okay, so the a's cancel and the negative signs cancel. So we have omega squared equals k over m. Okay, so we know that omega equals technically plus or minus root k over m, but negative frequency doesn't really have any physical meaning, so let's take the positive solution. Okay, and we'll also say that that we know that omega, right, equals 2 pi f, right? That's just got to know that relationship, of course, where f is the cyclic frequency in hertz, and of course omega is the radian frequency in radians per second. And this equals, like we just said, the positive solution for omega, right? So that's root k over m. So we know now, hopefully I'm not going off the page here, I don't think I am yet. So we know f equals, right, 1 over 2 pi, right, root k over m. And we know, of course, that f equals 1 over t, right? So we can say that t, the period of the simple harmonic oscillator, okay, is just the inverse of frequency here, or 2 pi root m over k, which is what we started with up here and what we set out to derive. So that's a pretty quick run through deriving the period of a simple harmonic oscillator. I'll probably do another example, another video where we do the derivation of the period of a pendulum as well. But this is a very traditional problem, very just fundamental, just good to know engineering problem, because a lot of vibrations and oscillations and waves and all these things kind of build on this fundamental principle of oscillation, and acceleration back and forth and all these things, and then you can start talking about damping and things that make the period longer or shorter, and all these things, and there's a lot of practical applications and follow-up questions that come from there. So anyways, I hope this helped, and like I said, I'll go on to maybe one more video on this topic before we come back to optimization and move on to other things.